3. Alright, so just to go over my game plan, I'm going to start off by going through the things I didn't get to in 1 and 2. Everything beyond maybe torque and angular momentum, and then torque, angular momentum, and then some oscillatory stuff, but not too much on the oscillations because it's not particularly difficult for it. And then we'll finish off with a little bit of fluid stuff. Okay. After I do that, I anticipate that only taking about half the amount of time that I've scheduled. So after I do that, I'll be opening the floor to people who have, hopefully some of you at least got a chance to go over your exam 1 and your exam 2. And if you ran into some trouble, right, if you had a problem and you weren't quite sure what to do or weren't quite sure how to handle, then we can answer them together and try and make sure everybody understands where they went wrong on the problems in the first 2 exams. Okay? So, alright, so let's go ahead and get started with torque. Okay, so, definition of torque, I'm going to label tau. That is equal to R cross F. But that is not descriptive enough, right? I need to understand what is R, what is F, what's going on. As soon as someone says torque, then you need to ask about what axis, because you can calculate the torque about whatever axis of rotation you feel like. If I have maybe, imagine this is like the top view of a door, and the hinges are on this side. So the door is going to rotate about this axis. I apply a force to the door. That is, let's say I apply a force. Right. So what R is the vector that points from my axis of rotation to the point at which my force is applied, and F is the force vector. But again, I need to know what axis am I calculating my torque around. Am I calculating my torque around the hinge, which is totally reasonable, in which case this vector here would be R, this vector would be F, and the angle between them, and they make, would be this angle theta. And we know from the magnitude of a cross product that if I say tau, which is equal to the magnitude of the torque. It's kind of shorthand for this. That's equal to R times F times sine theta. Okay? This is what we'll be using almost universally, because the fact that torque happens to be a vector is not of enormous utility when you have motion that only occurs in a plane. So all of the torque stuff that you'll see takes place effectively within a plane. So it's not really a 3-dimensional thing that's rotating around. It's really more like a 2-dimensional picture, something that's occurring on the surface of the whiteboard. So in that sense, the fact that it's a vector is not really that important. It'll just be pointing, strictly speaking, this vector R cross F would be R cross F pointing out of the whiteboard. If you remember how to use your right-hand rule. But again, that's not really that important. So rather than define and think about torque as going out of the board or into the board, which are my only 2 options if it's a 2-dimensional problem, I would rather think of it as positive torque and negative torque. And my definition is going to be a torque that makes the system right? This is just for reference over here. A torque that makes the system, that wants to make the system rotate like this, is a positive torque. And a torque, is a negative torque. And this guy, that makes it want to rotate counterclockwise, would equate to a positive torque. Okay, so just for reference, when I say positive and negative torque, that's what I mean. A positive torque is trying to make the thing rotate counterclockwise, while a negative torque is trying to make the thing rotate. In real life, though, a positive, or I'm sorry, a torque that makes the system want to rotate this way is a torque that's pointing out of the board. And a torque that makes the system want to rotate this way is pointing into the board. So really what we're doing is we're defining positive is this way and negative is this way. But again, because the vector character of torque is not really that important for this, then we can just define positive and negative this way. And one more note, it doesn't matter if you define it this way or the reverse. It's completely irrelevant. You can do whichever you feel like. But you should be consistent so you don't make mistakes. Just pick one. And the common choice for most people is this, because this is what is referred to as mathematically positive. So this would be a good way. But we'll float you both. Okay, so anyway, back to this problem. So the torque about the axis is the length of this vector r times the magnitude of this force F times the sine of this angle. But I could also ask, okay, well, what's this about this point? So same door, same hinge, everything's still the way it was before. I apply the force to the same point. This is F. But now I ask, what's the torque about the center of the door? So if I want to know what's the torque with respect to this axis, then the vector r would be different. It would be this. Would be my r. My f and my sine theta would still be the same, but r would be half as much. So the torque about this axis produced by this force is different than the torque about this axis produced by the exact same force. So whenever someone says the word torque, you say about what axis? Also, one more slightly weird and abstract note, but still true and reasonable. What if I want to know the torque about this axis? Can I do that? It's not even on the door. Is that fine? Or is there a particular reason why I can't calculate? If I apply force to this door about this point, can I calculate torque about this axis rather than the one that's actually on the door? Is that okay, or is there a reason? Shout something out. Certainly draw an arrow, right? Yeah, I didn't need to make it that linear. The torque about this one. So I can certainly just draw an arrow here and call this arrow R and F. Fine. Right. There's no reason why the axis I have to calculate the torque with respect to has to be inside the object. Absolutely none whatsoever. Right? So I can calculate torque about any axis I feel like, whether it's in the thing or not in the thing, far away or close, whatever I want. So one force produces one torque. So when you're summing the forces on an object, obviously you calculate all of the forces that are acting on it, add them all up like vectors. When you calculate the torques that are acting on an object, you have to add up all the torques with the appropriate positive and negatives. Okay, so definition of torque is all good. So let's try this. So if I have let's say, I don't know, a wheel. Yes? And I apply a force to it. It's F. And I want to know what is the torque about the contact point. What's the torque about this spot? That's due to this force. What would I have?
Zero.
Right? Because in this R cross F, R is, there's nothing, it's right there. So R would be equal to 0. It would be immediately acting on that point. So there is no torque produced about this axis by this force. Okay? But what about here? So if I'm no longer asking about the torque contact point, if this is a disc wheel of radius r, okay, then the axis I'm interested in to the point at which the force is being applied is this one. It's clearly got a length of r. Right? The force I'm applying is F. And what is the sine of that angle?
9 degrees.
Right. The angle is 90 degrees, so the sine of the angle is 1, and this is just the torque. Right? Is it positive or negative?
Negative.
Okay, a couple of examples. So, let's actually do a problem with it now. So let's look and try and investigate the situation with this now. I have exactly the same thing as I just showed you. Right? When I have a disk, same radius r, but it's not really a disk now, it's a yo-yo. Okay? And there's a string wrapped around it. The string looks like this. And it's maybe, let's just say it's connected to the ceiling. So this represents a string that's wrapped around the thing and it can't slip at all. So I start off just holding this disk here. Okay. And then I let go. I release it and it starts to fall. So my question is, how fast will it fall? So with what acceleration will it move? Is going to use something called a no-slip condition. And you are all familiar with that, but I will restate it. For a no-slip condition, it says that if I calculate the angular velocity of this disk, and I calculate the, so if I calculate the angular velocity of the disk with respect to, let's say, the center, doesn't matter which point I calculate with respect to, but let's imagine that we're just talking about, so how fast is it spinning this way, okay, in radians per second. And the distance, the velocity of this point on the wheel, this spot on the edge, is equal to times r. Okay. That looks kind of like a restatement of something that we said before, but it's not. It's very important that you understand that it's not. I'll give you a slightly better illustration of the no-slip condition, imagining a wheel just rolling on the ground. So if I say this wheel is rolling, not slipping at all, not sliding, but rolling, and its center of mass of velocity is v. So we have something like v center of mass, right? That's just moving in a straight line like this. Then that means that the velocity of this point with respect to this guy is, I'm sorry, not with respect to this guy. Oh, right, I'm sorry. So what that means is v center mass is equal to theta dot times the radius of the wheel. Okay? So what you should understand is that imagine the thing wasn't rolling at all. If it was just perfectly static, there was no rotation, it was purely sliding along. In that case, the center of mass would obviously be moving, but there would be no angular velocity. Right? So this wouldn't be true. Imagine that it was a car skidding out. Right? So it was slipping, but in the other way. So it was sliding, it was rotating really, really, really fast, but not actually moving all that quickly in terms of translation. In that case, this would be really big, but this one wouldn't be. And so what you'd have is the other way around. So rather than having this being too small, which is the case if I'm just sort of purely sliding along, I could imagine burning out, in which case my velocity center of mass is not large. It's not as large as theta dot times r. The no slip condition is the exact meeting of those two, which is to say, it's not sliding forward, it's not sliding backward. It's just nice and rolling along, nicely sort of rolling across the ground. And in no way is there any slipping. Another way you can put that is the friction between the wheel and the ground is static friction rather than kinetic friction. Because static friction doesn't mean that the objects aren't moving. It means that the surfaces that are in contact with one another are not sliding with respect to one another. Okay? So when I am holding the pen like this and moving, even though my hand is moving and the pen is moving, the coefficient of friction, or the frictional force between my hand and the pen, is static, not kinetic. Even if this thing is rolling across the table, if it's not sliding, then the frictional force between the table and the pen is still static, because instantaneously the bottom of the pen that's touching the table and the surface of the table are not sliding with respect to one another. So that's the difference between static and kinetic friction. So another way to say there's no slippage is to say the frictional force between the ground and the wheel is purely static. So I have this guy in a no slip condition. Where can I go? Well, a good place to start, right, when we don't really have a plan to go through, is Newton's law. So we can start with saying that the sum of the forces on the thing is probably going to equal this, and the sum of the torques on the thing is probably going to equal this. It's going to equal that. So these are the two big ones, which are actually the same equation but in slightly different forms. And they refer to, respectively, the translational, that we say that the sum of the forces on an object is equal to ma, where a is the acceleration of its center. Okay? The torque we can specify about which axis we're calculating, but there will be obviously better choices than others. So let's figure out what to do. So let's identify all the forces that are acting on this thing. So I will redraw the picture over here, so we can just add up all these forces. This. Let's see. Okay. So what are the forces that are acting on this guy?
Gravity.
Gravity. Where is it acting?
Center.
Center. Right here. So this would be mg. All right, what else?
Tension.
There's a tension force in there as well, right? Tension force here. So, cool. So those are the two forces that are acting on the thing. What torques are acting on the thing? Again, now we have to say about which axis. But the axis that we're going to talk about is the center of mass. So we're going to ask, what are the torques about, say, actually no, let's sum up the torques around this point. Let's see what happens. So here's the axis of rotation that I'm talking about. Here's the point about which I'm going to sum my torques. And so which of those two forces apply a torque around that axis?
Gravity.
Gravity, right? But the tension doesn't, right? Because it's acting right on that. So if we choose this spot to add the torques around, then this does not play a role, and we only have mg. That's an excellent choice, because do you know what the tension is? Yeah, me neither. We would have to solve for that first if we wanted to include it, which we could do, right? And it'll end up coming out anyway. But if we choose to put the axis of rotation about this point, then the torque, the tension disappears from the equation. So I actually don't need to solve for it. So the torque, so the sum of the forces, is the tension minus mg, and that's equal to m a center mass. And the sum of the torques this point is just torque that is contributed by this force. Is it positive or negative?
Negative.
Minus magnitude of the force is what? And the distance would be r. And the sine of the angle would be what?
90.
90 degrees. Well, the angle's 90 degrees, so 1 again, right? So this is the sum of the torques. But what is this? This is equal to I times a double dot, which you could also call I alpha if you're so. But what is our, again, no slip condition here? It's that the velocity, if we're talking about making our axis this point, the velocity of this spot with respect to this point is going to be this. So I can replace, with and the derivative as well. So alpha is equal to, so A is equal to double dot. So in this equation, I can replace theta double dot by A over R. Okay. And this A is and so, solving for all this, right, I can say that the A center mass is equal to minus m r squared over I. Cool. And what is the moment of inertia of the disk? If it's just a uniform solid disk,
One half mr squared.
m r squared over 2. And so this would be equal to minus m3r squared over mr squared divided by 2 is equal to just a minute.
Wouldn't that be the inertia about the center of the disk, but we're not going to
Yes.
There you go.
Thank you so much. That's so stupid. Yes. You're my favorite. Just for the next like 10 minutes, you're my favorite. Okay. That's actually mildly embarrassing, but yeah. Right, so she made a good call. This I is not the moment of inertia about the center, right? This is the moment of inertia about this one. So, what should we have? This should be I is equal to the moment of inertia about the center of mass, which is mr squared over 2 plus mr squared, which gives us 3 mr squared over 2. There we are.
Could you tell that didn't make sense? Just trying to look at the answer.
Oh, because it shouldn't accelerate faster than if it was in free fall. That would be silly. And so, if we plug this in, because now I'm going to randomly rebuked, this is equal to minus mgr squared over 3 halves mr squared, which comes to a grand total of minus 2/3. That makes more sense, right? And so we find the thing that accelerates not with minus g as it would in free fall, but with minus 2/3.
So we have to.
Okay, so with less, about 67% of what it would if it was not yeah.
Plus the distance.
Because we've defined this to be positive. So my sort of self-consistent sign convention is this is positive, this is positive. And if you hold those things together, then yeah.
So that I just like
No, see that's the thing. That is the sort of, it's important for you to recognize that. That is the beauty of this choice. Right? Because we made this choice, we've eliminated the need to find t at all. So this is not a necessary equation because we were smart about where we chose the proportion. I'm going to do this again one more time. I've calculated it out here. And we'll get the exact same answer, but we'll find that we have to use
4. I go past 4 hours. Pump through like more than half of the final
it's whichever axis. So if we're talking about this is the velocity of the point, this is the distance between the point and the point. So the velocity of this spot with respect to this point of contact is theta dot. The velocity of this spot relative to this term is theta dot times r2. So it's sort of it gets kind of confusing, but the idea behind the no-slip condition is there is a point at which two surfaces are in contact. We call that the point of contact, right? Where the two, whether maybe the string and the wheel are touching, or maybe if you have a disc rolling on an incline, the spot where the disc and the incline are touching, whenever you have two surfaces in contact, that is the point of contact. The velocity of a particular point on the circle, or on the disc, is equal to the angular velocity of the disc times the distance between the point of contact from whichever spot you're talking about. That is the no-slip condition.
So I'm trying to kind of ridiculous, but you're stuck on a problem or something. Just like write down the second line. So
Yeah, because that's always what it is.
okay.
He mentioned that, I think, and he was actually telling the truth. Literally every single thing you will ever do is fundamentally coming from F equals ma. Even this is F equals ma, cast in a slightly different form.
So you write it down.
Yeah, just write it down, add forces up, add torques up. But now that we've gotten a little, yeah.
Just feel like if a problem says like, oh, it's not slipping, you know that like these people are saying that are
Yeah.
know
Let me restate that one more time. So let's pretend I didn't say anything about the no-slip condition. Let me restate that one more time in as clear and reasonable language as I possibly can. So the content of the no-slip condition, and I'll explain now why it's different than the V equals omega R that we are used to using. If I say there are two surfaces that are in contact. Thank you. Then the velocity of the center of mass of the rolling object, this velocity v is equal to the angular velocity omega or theta dot, is the way I've been calling it, times the radius r, because the distance here is the distance between the point of contact and the point that I want to know the velocity of. So if I spray paint a little dot in the middle of this disk, the velocity of that dot, the speed with which that dot moves, is going to be theta dot times the distance from the point of contact, which in the case of the disk is r. That differs from the normal, normal relationship, because I'm not talking about, because this essentially relates two surfaces, or two objects, not just one. So it relates the speed of the center mass of the rolling object to the point of contact with the other thing. Okay. So it's possible, for example, that the point of contact doesn't move, but the thing is rotating because, like I said, it's sort of burning out. That's a possibility. Another possibility is that point of contact is moving, but it's not rotating at all, in which case like, you slammed on the brakes and are now sliding. But the no-slip condition says that the velocity of the center of this thing is equal to angular velocity of the thing as it rotates times this distance from the point of contact. Okay? Yeah.
So like if it was asking for the velocity of a point that is like not at the center, would they have to like ask you like a specific time?
So yeah, because the velocity of a point not at the center is going to be constantly changing, right? Because if I asked you for the point, what if I asked for the velocity of this spot? If I just sort of draw a profile of that one spot as this thing rotates, you know, it starts off here, it'll then go here, and then it'll be here, and then it'll be here. So if we're talking about the motion this way, like just the horizontal motion of this thing, then the velocity of this point here will be this way. The velocity at this spot will be a little bit less. When it comes to the back, the horizontal velocity for that instant that it's sort of just coming up behind is 0 because it's all sort of going up. You know what I mean? So if it's not at the center, the same thing is true, but this R is changing with where it rotates. The thing about the center, and the only place you'll ever really use it, because I've never used it, is talking about the center of the thing, because that center, the distance is going to be constant the whole time. It'll be like a uniform disk, or a cylinder would be the same thing. So that's just a slight, hopefully, clarification of the no-slip condition. And so, let's do this problem again, real fast. But now we're going to sum the torques about the center, which is what I was going to do originally. And see what happens. So I'm not going to make this choice. I'm going to make the perfectly valid choice to sum the torques around this one. The sum of the forces is again the same. 2, tension up, minus mg down. And this is equal to ma center mass. But the sum of the torques is now the sum of the torques about the center. And the sum of the torques about the center, I no longer have to consider mg, because it's actually right on the point that I'm looking for, but I do now have to consider t, the tension. And so now I have to say this is the tension times the radius times the sine of 90 degrees, which is 1 again. And again, this is trying to make it rotate this way, so I'm going to need another minus sign. And this is equal to I times theta delta. Notice, though, that now both equations involve t. So I'm going to have to eliminate the tension somehow. So the way I'm going to do it is I'm going to say, okay, I would say T is equal to ma center mass plus mg. That is the first one. And so the content of this equation has been exhausted. That's sort of a good idea sometimes, by the way. When you've exhausted the content of an equation, cross it out, put a line through it. Because what people tend to do sometimes is solve an equation and then later on use that same equation and they end up getting like 3 equals 3 and that's because you tried to solve the same equation twice and you end up getting the same thing on both sides. So once you're finished and you've exhausted the content of the equation, make a little mark so you know that you've done it. So this is the content of the first equation. The content of the second equation is that T is really equal to I theta double dot divided by R. So I can now, if T is equal to this, and T is also equal to this, I can just substitute in now. So therefore, I find that here, ma center mass is equal to, or I'm sorry, plus mg is equal to minus I big double dot over R, and because of that no slip condition, that's equal to minus I A center mass divided by R squared. Okay. So I have an A center mass over here and an A center mass over here. So I have to say, all right, M A center mass plus I over R squared times A center mass is equal to minus mg. I can cancel m out and I get that A center mass times 1 plus I over m R squared is equal to minus g. But I over m R squared, as we said before, right, is equal to I get, sorry. Oh yeah, but I just need to make sure I didn't miss something quick, because again, man, these guys are tricky as hell. So let's go back and let me just check this real quick. So F minus mg is MA. Works is this. Alright, so I get that. Okay. Go here. So the moment of inertia I is, what do we say? So now it's, oh right. So now what do we got? So now, unlike before, the moment of inertia is not the moment of inertia about this point, it's the moment of inertia about this point. So we don't have to use the parallel axis theorem this time, because we're simply talking about the center. And so I is not equal to 3/2 mr squared, but it's equal to 1/2 mr squared. So this equation becomes m, well, I'm factoring out the a, plus 1/2 m times a center mass is equal to minus mg. And canceling the m's and dividing, I get pleasantly enough that a center mass is equal to minus 2/3 g. Cool. Okay. So it worked out. It was fine. But notice that we can do it whichever way we feel like, but we have to be self-consistent when we do it. We have to use the correct I. We also have to use the correct angular acceleration, all that kind of stuff. So as long as we are self-consistent, as long as we're using the right moments of inertia, things like that, we can do the problem however we feel like. We can do it about here, whatever. But we saw that the first one was actually a better choice, right? Because we didn't have to use 2 equations, we only needed the one. Typically, you would like to choose, if possible, there's going to be one of the forces is going to be more irritating to calculate or to write down than the others. And so, if you can, try and place the axis about which you're summing your torques at that spot where the unknown force is acting. So you can eliminate it and you only need one equation to solve the problem. Otherwise, you're going to have to use 2. It may be that 2 forces are irritating to calculate and you're going to have to just make a choice. But if you can, try and make your life a little bit easier. All right. Cool. So, I have staggered my way through that, but hopefully I haven't confused you a little bit even more. Do you have any questions about that? Either the first or the second example that we did for the angular momentum. Yeah.
Yeah, so you made the down direction.
No.
Because
No, I defined.
I don't get how the acceleration is in opposite.
Oh, I don't. My G is just 10. Alright, so the force of gravity, so the acceleration that I feel if I drop an eraser is minus this, minus G. I don't like hiding minus signs inside. You know what I mean? Because it's just makes everything bad. Because if I did that, then I would have to say this was the force from gravity, but with the implicit understanding that G is negative. Which, you see what I mean? So I like my constants are just numbers with no minus signs. And so I insert the minus sign when I say it's acting down. So the answer would be, that's 2/3 of 10, like 7-ish. Okay, anything else? Is that good? Okay. So, we'll move along to angular momentum. So, force we found out earlier, right, was equal to we said before that force is equal to the derivative with respect to time of the momentum. Similarly, we can write something for t. Now, watch what I do. So I say the torque is equal to R cross F, which is equal to R cross TP. And now I claim that this is equal to Does anybody have any objections to me just pulling that derivative out? Or if you don't, can you see where somebody might accidentally have, at first glance, have an objection to me just pulling that derivative out? Yeah, right? Because I'm sort of neglecting completely the product rule.
Yeah.
Because if I expand this, this is equal to
Yeah, so it makes
right?
sense.
So I seem to have made a misstep, but I haven't really. You know why?
Is it about the center of that?
No, R is not constant. R is the position of a particular point on the object, or point might be moving. Yeah.
The distance from the axis to the point is not changing?
That's true, but even if the distance isn't changing, the vector can still change. So the thing is, here's the thing. I say that this is equal to this, but this is not 0. How can that be? Yeah.
Is it because like the sine and cosine parts of 3?
Yeah. Look. This term becomes so the derivative of R is the exact same direction as P is. Vectorially, they're the same. P is multiplied by a mass. So the direction, the angle between those two vectors is 0. The angle between V and P is equal to 0, because one is just m times the other one. Which means that this cross product goes away. This is equal to 0, even though neither part was equal to 0. That's the weird part about a cross product that's really important. Or any kind of vector product. It's possible to have the product of two vectors equaling 0, even if neither of the vectors themselves are equal to 0. For a cross product, it's if they're collinear. For a dot product, it's if they're perpendicular to one another. But it's entirely possible to have a cross product that cancels even though neither part happens to be equal to 0. Anyways, so this gives me that, and so I give this a definition. I call this L. say that this is called the angular momentum. Right? So torque equals the rate of change of the angular momentum in the same way that force is the rate of change of the linear momentum. So I use angular momentum in essentially the same way as I use linear momentum. So I'm not going to do that a lot because I've already gone over that with my second. I think you've all done it a bunch of times. You know, classic problems like you have, a kid jumping off a merry-go-round is one that we used, right? Where the kid has some angular momentum this way and the wheel will rotate the opposite way. Things like that. They're present in your book. They're in the lectures you've done. So I'm not really going to touch on those. But I am going to hit some of the finer points of angular momentum, even though it's not particularly computationally difficult to use the way that you'll be asked to use it. Okay. So if I have the angular momentum L equals R cross P, I could also rewrite this if I feel like as being M times R cross P. What's R again?
Position.
Yeah, but with respect to what?
The derivative of
Yeah, but like position relative to
What's rotating?
wherever I feel like it, right? That's the answer. Again, just like torque, about which axis? Angular momentum, about which axis? Right? The angular momentum about any axis can be calculated. In the same way that I can calculate the torque on the door about a point that's not even on the door. I can calculate the moment of inertia of an object about a point that has as far away from the object itself. So if I had, for example, a point, or this will be like a planet, say, and I had a moon orbiting it, let's say it's moving in a circle, I can calculate the moment of inertia, I can calculate the angular momentum of the moon. This is a moon, this will be a planet. You know what? This is going to be a black hole. This is going to be a star. How about that? This will be a star. This will be a black hole. Okay? I can calculate the angular momentum of the star relative to this axis. So if I say, all right, I want an axis about here, what is the angular momentum of the star? R would be this vector. And and V would be the velocity of the star. So if it was rotating in a circle, maybe V would look like this. And so, the angular momentum in magnitude about this axis, the angular momentum of the star about this axis is equal to this distance, which would be, call it R sub O for the orbit, is the orbital distance times the momentum of the star, which is the mass of the star, times the velocity of the star. And because it's moving in a nice circular orbit, this angular momentum, the angle, theta, is going to be 90 degrees. And so I have this. Slightly different question now. What if my orbit wasn't circular? Could I calculate the angular momentum still? What if my orbit was like this? So the orbit isn't circular anymore. It's like this weird ellipse, a flattened circle. Can I still calculate the moment of inertia? Yeah. If I know the velocity v here, and this distance, which I can call r, again, the moment of inertia at this point, right, when the star is right here, the angular momentum L is equal to this distance r times m star times v star. Same as before. But let me ask you this question. What is the value of the angular momentum here? I figured that out. Same thing. Why would it be the same? So, the angular momentum here is the same as the angular momentum there because of the law called oscillation of angular momentum. So what is that? Remember that the law that we have is that the relationship that we have is that this is equal to the torque. And so, if the force that's acting on this star is from the black hole and only the black hole, and if this is the distance r, this is vector r, if the force is along that force, or that position vector r, then the torque becomes r cross f is 0 if r is parallel to f. Okay? So, it turns out that in the case of the conservation of momentum, we said if there are no external forces, then the momentum of the system is conserved. In the case of a rotational system like this that we're talking about, if there are no external torques, then the angular momentum is conserved, but that doesn't necessarily mean that there are no external forces, right? So there can be forces acting on this thing, but the angular momentum is still conserved if the forces are along the line that connects the things that are exerting the force, right? Which is almost any force that you can possibly think of. Think of a gravitational force, for example, right? So you take planets in orbit around the moon. At every point, it's attracted. It's pulling the moon towards the planet, and so it's conserving angular momentum. Electrostatic forces do exactly the same thing. Okay? So there is a direct analogy between linear momentum and linear force and angular momentum and torque. But the conservation of angular momentum is even more general than the conservation of linear momentum, because I'll sort of write it in a little bit of a hierarchy here. It's important that this be a point that sort of sinks home, is that conservation of energy, conservation of angular momentum. What are the requirements for the conservation of energy? So under what conditions is energy conserved?
No non-conservative forces.
Huh? Kind of, yeah, but that, you can imagine if I have my closed system is like a giant box, and in that system there's a rough ramp and a block that slides down it. Energy isn't certainly conserved even though nothing is left in my box. So in that case, it's not true. So what is the conservation? It's related to what we did last time, right? When we had the work and energy relationship. You can remember, what is the change in the total energy equal to? Not the network system.
Non-conservative.
Non-conservative, right. So conservation of energy relies on no non-conservative forces. The conservation of momentum, of linear momentum, what is the requirements of that? No external forces. No external forces. So is it possible I'll put it this way. So is it possible for momentum to be conserved even though energy isn't conserved? An inelastic collision. Anything but an elastic collision. Momentum is conserved but energy isn't. So in that sense, this kind of subsumes the conservation of energy. They're not equivalent in that way, right? So it's not that, I'm not saying that anything that conserves energy conserves momentum, because that's not true. But what I am saying is, in most systems that you'll be dealing with, like on your exams and as you come up, as engineers, when you're working with systems, very rarely is this ever actually true. Like normally you have to account for some kind of dissipated forces or some kind of frictional forces. So this is usually kind of a general guideline, but not 100%, in mechanics. Thermodynamics is different, but in mechanics, this is rarely exactly true. But the conservation of linear momentum only requires that things are colliding with one another, or that things have internal forces but nothing external. So anytime you have a collision between things, this is conserved. Well, in general, this won't be. Lastly, the conservation of angular momentum says that any external forces must be parallel to which is the vector connecting the thing applying force to the thing where the force is applied. So in this case, we do have a relationship where if it conserves linear momentum, it absolutely conserves angular momentum. It has to. It must. For a planet in an elliptical orbit, kind of a moon, or a planet or a black hole or something, and a moon that's orbit looks like this. Its momentum and its speed, for example, not only obviously its direction is constantly changing, but even its speed is changing. Here, it's moving at the speed that it is here. Out here, it's moving slowly, and here, it's moving quickly. So in that case, obviously, linear momentum is not conserved, because there are external forces. There's the gravitational force from the planet, or the black hole, or whatever. But angular momentum is conserved, because even though there are external forces, they're all acting straight inward towards the thing that's applying the force. Okay? So this is sort of a hierarchy that you need to be comfortable with. Okay. So the last thing I want to do, I'm going to do one angular momentum problem, and then I'm going to touch on some of the fluid stuff, and then if you have any questions for me, we can ask. So the one angular momentum problem is, I remember this problem distinctly because one of my friends, his name was Kyle, who was a student at Dartmouth while I was at Alabama, and I was supposed to be the one that really liked physics and was into it, but Kyle has always been really smart in all the classes he ever took. And so he said, I'm taking an intro physics class, I have this problem for you. I was like, oh, okay. Walking in, like, I'm hot shit, because I've taken 2 years of physics major training, business major and econ major at the time. So he says, all right, so imagine that you have like a perfectly smooth frictionless surface, like an ice hockey table or an ice rink. Ice hockey table? Air hockey table. Okay, and on that ice skating rink, you have a rod of length L. Oh, and I'm not going to make it L. How about a rod of length little L. And you also have a lump of clay. So this guy has mass, let's make it M, and this guy has the exact same mass, also M. So these M's are the same. And this guy comes up, and he's sliding along with some speed V. Called V naught. And so the problem is, they hit, they collide and they stick together. So it comes in and it sticks to the end of the rod now. How does it move once it's collided?
In an angular way.
And I'm an idiot, I did not know. How does it move when it collides? It's not an easy problem. So I'm not going to ask for a lot of input, I'm just going to sort of show you, but hopefully what happens is you see how we connect the conservation of momentum and the conservation of angular. So I'm really going to decouple the motion to two things. I'm going to ask, how does it translate? And I'm also going to ask, how does it rotate? And so that way we can sort of picture the way it's going to go, and I can sort of draw a little diagram. So the first thing, what's the momentum? It's equal to mv naught. That's it.
That's the
The total momentum of the system. Only mv naught, because that's the only thing that's moving. Mv naught. And it's in. I'll give it a little. So initial momentum, mv naught in the x direction, nothing in the y direction. And what's its initial angular momentum? About what point? I'll just make it scalar L. Initial angular momentum? To what? What do you think? What could it be? Well, let's pick an axis that's smart. We'll pick this one. So right in the center of the rod. I think it's just so what is the angular momentum about that point at the very beginning? Yeah. It's going to be, okay. Well, we're going to have, it's not going to be zero, right? Because this thing isn't moving, so it's obviously not contributing. So this guy contributes. It has an angular momentum at that point, right? Because it has vector r. And we also have v naught, but we're going to have to deal with an angle in here. That kind of sucks. So we don't know what that angle is. But watch. It's equal to the momentum, which is mv naught, times the distance, which is r, but we have r times the sine of theta. And what is that? Look at it. Can you see it? What is r, this distance r, times the sine of this angle? See? And so you can see that really you only need to calculate the angular momentum by multiplying the mass times the velocity, the initial momentum of the thing, times the sort of perpendicular nearest distance, if you like, something like that. Cool, so we have this initial linear momentum and initial final or initial angular momentum. But here's where it becomes kind of difficult now, is we're saying, all right, so this is the initial momentum, what's the final momentum? And it's going to be complicated. And the reason it's going to be complicated is because it's not going to rotate like a nice, like this. It's going to be sort of weird, like it's going to because one end is heavier than the other. It's not got a nice constant acceleration, or a nice constant rotation like that. It's not going to be free that way. Yeah.
What was the sine of theta L over 2?
The sine of theta isn't L over 2, but r times the sine of theta, because the sine of theta is this divided by this. So this times the sine of theta.
Okay.
So this is our initial momentum. But this is the momentum. This is the total momentum. But you know, watch what I'm going to do. I'm going to calculate the momentum of the center of mass. What does that mean? So the total momentum P is equal to the sum of the momenta of the individual parts, which is equal to the sum of m times v of the individual parts, which I'm going to write one more time as sum And so, this is equal to, I can bring the derivative outside because it's just a sum of a bunch of things. Is this beginning to look vaguely familiar? What am I going to pull out? I'm going to say this is equal to capital M, which is the sum of all the masses, the sum of all the masses of all the parts, times d by dt of sum of mi ri by phi. How about that? Does that look familiar? What is that?
Center of mass.
Center of mass. This is equal to M times R. Alright? So, here's the kind of weird, sneaky part of this, okay? The total momentum is equal to the mass times the velocity of the center of the total mass of the entire system times the velocity of the center of mass. And this is the thing that's conserved. This guy. So, watch what happens when I show you how the center of mass is actually moving. Here's my rod. L over, got that length L. There will be 3 positions that I'm going to sketch. 1, 2, 3, and then once more when it's right there. And once it's connected. Where is the center of mass when it's right here? How do I find it? What do I do? Yeah, the center of mass of the system. What do I do?
Oh, it'll be R everywhere.
On what?
It'll be
I made these guys have the same mass for a particular reason. I just need to draw a line between the center of this and the center of this, and then halfway along that line is going to be where the center of mass is. So in this case, the center of mass will be right about here. In this case, right about here. In this case, right about here. Good. We thought initially that the center of that the initial momentum was moving purely horizontally, right, in the x direction, and it turns out it is. As you can see, this guy, the center of mass is a point that's moving that way. Once it becomes attached, though, now the center of mass is permanently this spot on the rod. Okay. Once this guy, remember, this is the real thing, the hollow circles. The filled-in dots is the location of the center of mass. Once it collides, once the actual object collides up here, the center of mass is now permanently this location on the rod. And so if this is conserved, then as the thing moves around, this spot must continue moving that way with exactly the same momentum. Okay? So I can draw a picture of what's going to happen. And then move along here. So it hits for a little while, maybe it looks like this. And then maybe a little more.
Third time's the charm.
That, and then this guy might look like this. So that's how this thing is going to go. You see how it's not moving in a nice, just like sort of way. It's like this end is sort of flinging around really fast, and this end isn't really moving that much because it is this point that must continue moving in this straight horizontal. Okay, so qualitatively, that's what it'll look like. How fast will it be rotating? Easy, because we know how fast it'll be moving. We know how quickly this spot will be going because we know the initial momentum already, right? The initial momentum is m times v naught. It's pi. And then p final is equal to, so now what's moving? The mass is 2m. The velocity is v final, which we don't know. And it turns out, therefore, that v final is equal to v initial over 2. So if this guy comes in with speed 10 meters per second, it collides. The total sum, all both of them together, will translate this way with a translational velocity of 5 meters per second. How about the angular velocity? Well, the initial angular momentum, L sub I, is equal to, what do we have? We said mv naught times little l over 2. How about at the end? About which point? How about this point? We can calculate the moment of inertia about this point, right? So L final is equal to the moment of inertia times a dot about this point. I'm not going to do it because we've done that before. But once we calculate this moment of inertia, which is not, of course, ml squared over 12, which would be here, nor is it ml squared over 3, which would be here. It's in between. On the exam, we had it switch, we had it sort of like turn away, ml squared over 9. So it's something in between there. But we can find that at the end of the day, theta dot, this will be conserved as well, and we find that this is mv naught L over 2i, whatever I happens to be. Okay? So by splitting it into translational motion and rotational motion, we solve the problem. We know exactly what it's going to do. Yeah?
How would you find the inertia of the system afterwards? Because the long right at the end. So
You would just add them together. So the moment of inertia of
of the ball and then of the stick and that ball. So do mr squared plus
Linear.
yes. Well, m L over 4, m times L over 4 squared would be the moment of inertia of this guy. And then you have to calculate the moment of inertia of the rod about this point as well. Okay. So that's what I mean by decoupling. So it's a problem that I didn't know how to solve when I was a second year undergrad, but it's an important one. The way you understand that, the conservation laws hold true separately, but simultaneously. Okay, so let's do some fluid stuff, and then if you have any questions, maybe I can do that. Otherwise, feel free to go after that while I'm here for you to help it. Reason so? Fluid stuff, yeah. Sorry.
One question about the last one.
Yes.
How did you know the angular momentum was conserved? Because it seemed like the force was acting in the same direction.
There were no external forces, period. All the forces that were acting were between the clay and between the constituents of the system. In that case, then both the linear momentum is conserved, which we use because there are no external forces, and the angular momentum is conserved because, of course, there are no external torques if there are no external forces. You know what I mean? But it's also possible, like one more time, that there are external forces, and so the momentum, linear momentum, is not conserved, but the angular momentum is still conserved because they act along the same direction as r. Okay. All right, so last bit will be fluids, and then call it a day for my talk. All right, so first, real quick, is the pressure with depth. So if I have a box say I have a box and it's floating in the water, or in the fluid, right? So this fluid has a density, rho, and it's constant. So every little volume of the fluid has the same mass. And so my cube has mass m. And volume, and the length of each side is A. If that's the case, then you may be familiar with the equation that the pressure at a particular depth is equal to the external pressure, which is like atmospheric pressure, plus rho times g times the depth, d, where the depth is this distance below. So it's defined to be the positive distance below the surface of the fluid. Okay. In depth d is the atmospheric pressure plus rho times g. And really quickly, the reason I'm going to show you why that is if you imagine that this is just pure water, and I'm drawing like a dotted line cube. Okay. Like that. Okay. So everything in here is water, but I'm just imagining that there's a invisible sort of cubic area in the center that I want to talk about for a second. And I want to ask, what are the forces on that cube? Well, I've got 6 pressures that are acting on the thing. And I've got also a gravitational force. So I've got a pressure from the top and from the bottom, from the left and from the right, and from the front and the back. So I have 6 pressures that I have to deal with. And I also have a gravitational force going down. So I have this pressure here. And then also okay? So I'm imagining this sort of, clear cubic area in the center of a jug of water, and I'm just talking about what are the forces on the thing. And what you get is the following. So if it's in equilibrium, which is to say if it's not swirling around and it's basically static, then the sum of the forces on it must be 0. Does that make sense? Is that fair? Right? So what that means is, thinking of the purely front and back direction, there is no motion there, so it's in the equilibrium there, which means the force coming from the front and the force coming from the back is the same, which implies that the pressure at the back and the pressure at the front are identical. So it doesn't matter if you move this way in the tank of water, the pressure stays the same. The same could be said left and right. So at a particular depth, whether you go left or right or forward or back, of course, the pressure is constant. You wouldn't expect it to be anything else. But what is not constant is the pressure in the vertical direction. So if I erase all the other pressures here, and I get only this. Now if I sum the forces in this direction, sum of the forces on my cube are, I have gravity, I have the pressure at the bottom going up. Bottom. So actually what I'm going to do is I'm going to say, let's say the top of the cube is at a depth d, or at a depth x. Let's just say. Okay? And so the force going up is equal, or sorry, the force going down is the pressure up top, which is the pressure at that depth x, times the area of the top, which is a squared. And the pressure from the bottom, that's the, sorry, so this is going down, so this is a minus sign. The pressure from the bottom is going to be equal to plus P of x plus A, where A is the n times a squared. And then we're going to have mg, which is also down, so minus mg. That's equal to 0, right? Because the sum of the forces on the box is 0. I'm going to rewrite this slightly differently by saying, I'm going to divide, or I'm going to keep it like this, and I'm going to say it's p of x plus a minus p of x times a squared minus mg. But mg is really the density times the volume of my cube, which is a cubed times g. And this is equal to 0. And so what that means is, if I divide everything by a cubed, then I get this, and I get this, g is equal to 0. And so this is this. Okay. So that's how that's derived. So, because this is constant, that just means that pressure at a depth x is equal to rho times g times x, plus the pressure when x is equal to 0, which we call the external pressure, or the atmospheric pressure. So that's the pressure. Okay? And so this is a quick derivation there, so you understand where that comes from. You can calculate the pressure at any depth you feel like just by using this. Okay. I don't really, there's not really a lot more to do with fluids, to be honest. You talked about this, you talked about, I think, the Bernoulli formula as well, but you didn't put a lot of emphasis on it, and it's not really, I don't think, probably worth any amount of time to do. So as long as we're good with that, I'll just list the results of the oscillator motion that I wanted to talk about, and then that's all the information I wanted to go through. Skipped over that, so I apologize. For oscillators, this is really the big thing to understand and remember. Simple spring. Simple pendulum. And simple pendulum. The only meaningful distance between them, there are actually two meaningful distances. Omega. For a simple spring, omega is the square root of k over m. For a simple pendulum, it is g over L, where L is the total length of the pendulum. And the physical pendulum is the square root of mg little l over I. To sort of recap what I'm talking about, of course, for a simple spring, a block of mass m and a spring with spring constant k. Angular frequency of oscillation is that, and the time period t is equal to 2 pi over omega. For a simple pendulum, those parameters that I'm talking about are, you have a mass at the end of a string of length big L, and this mass is m, although it doesn't matter, and gravity is pulling down with the force mg. So g is, of course, the gravitational acceleration, and L is the length of the pendulum, is the distance between the point, pivot point, and the mass at the bottom. last but not least, the physical pendulum, which is the most general of all the, which is like the general form of the simple pendulum, is that's what I just drew as a simple pendulum, yeah. Just a single point mass at the end of, I mean, it's just a ball connected to a point string. Most people, it's just that. Is that okay? Sorry. So here is the length of the string. So it's a little pendulum bob attached. So L is the length. And for a physical pendulum, this is where it actually gets a little bit subtle. So it's important that you recognize that the center of mass will be right here. Well, it may not be right there, right? It could be heavier at the bottom. It doesn't matter where the center of mass is. So let's be more general. Just say the center of mass is maybe somewhere down here or something. I don't know. For a certain form rod, it'll be at the center, but in general, it could be anywhere. The distance I, I'm sorry, not I, L. The distance little l is the distance from the pivot point to the center of mass. From the pivot point to the center of mass. Not the length of the thing, right? Not the distance above here, not the distance from the pivot point to the bottom, but the distance between the pivot point and the center of mass. So this is true for a physical pendulum that's a rod or a disc or a hoop or whatever you like. The center of mass is right here, the pivot point is right here, and little l is the distance between them. I is the moment of inertia about the pivot point. Not about the center, not about the bottom, nor about the top. I is the moment of inertia about the pivot point. So, for the physical pendulum, one more time, omega, which is the angular frequency, is equal to the square root of the mass of the physical pendulum, the whole thing, times g, times the distance between the pivot point and the center of mass, L, divided by the moment of inertia about the pivot point, I. So this is the point, this is the bit where everyone, not everyone, where a large number of people kind of dropped the ball on at quiz 8, right, was using the right moment of inertia. The moment of inertia about pivot. Okay? All right. So I know I just kind of hurled a lot of stuff at you this time, but we didn't do much in the way of numerical examples. But there's not a lot of numerical stuff on your exam, unfortunately. So this last one I wanted to sort of hit mostly symbolically and understanding how those derivations work. So if you have any questions about your quizzes or your exams that you've taken thus far, feel free to ask me about it. Do that now. If you don't, then you just like to go home. There are other people.
You going back?
But if you are going to stay, I'd like to do it kind of as a
Of what?
Hagerstown.
Why?
I got some cookies.
This is you guys in count.
You go back to you?
North Campus.
Physics.
I got practical exams.
And Friday I have linear and I'm gonna literally go. How is that? Well, actually, it's not that hard. It's really? That question. We always Are you guys ready for tomorrow?
I memorized 10 million equations. I know. We studied for like hours.
Oh, I
this, and then
So
I came here,
alright,
like,
so
oh my God.
you were sitting around.
I'm leaving.
Where was the yeah. Yeah, that's right. So I made a mistake with the ballistic pendulum problem we did. Or not the ballistic
You're gonna get
ballistic spring
I
problem.
always do.
So as you can see, you recognize I videotaped these. And so hopefully tomorrow I'll put them up so you can see them. And on the video for yesterday, I included a bit where I actually spliced out the part where I did the gun shear into the spring, and then I sort of redid it, and I spliced it inside there, so that'll be in the video there. I'd rather avoid doing that now, just because, you know.
Oh, I didn't know it was already up. So
Yeah,
I was just looking.
yeah. So I'll send the links out tomorrow.
Okay, what else is that?
Do you know if I need to know the constants and the radius?
No, you won't need to know the numeric constants. I mean, the simple, like G, you'll probably, but you won't need to know the weird numeric constants, like the capital G, for example, or the mass of the Earth and the radius. Yeah.
Did you do like the last problem from the last quiz?
Last problem from the last quiz.
Yeah, it's like the physical pendulum.
Yeah, so it was the physical pendulum problem. So if you recall, the moment of inertia about the pivot point, which was 1/3 of the way from the end of the rod, right? The moment of inertia I about this point, so we had something that looked maybe like this, and then here, here's the pivot. So we would define this to be our angle. So as long as the angle is small, which it was in that problem, the angular frequency is the square root of mgl over I. L, in that case, the center of mass, because it was a uniform rod, was right in the middle. And so L was the length of the rod, which if this whole thing is big L. This is equal to the square root of mg times big L divided by 6. Because that's the distance here. That is what little L is. And I divide that by the moment of inertia I, which was mL squared divided by 9. That was the correct moment of inertia about the pivot point. And so canceling, L, I get this is equal to the square root of 3g over L. Oh, sorry, 2L. Okay. And so the time period t is just 2 pi over omega, which is 2 pi times the square root of 2L over 3g. So that was the answer to that.
What did you do wrong yesterday?
But for the ballistic pendulum,
Yeah.
When you have a pendulum or a spring system that's hung vertically, in terms of where it oscillates, the distance that it's stretched is going to be longer. It's going to be longer than if it was just sitting flat on the table, because there's a gravitational force to work in. So what that means is the length, all it really does is it shifts the equilibrium down, right? So rather than being an unstretched length of 10 centimeters, it might be an unstretched length of 15 centimeters, because now there's a gravitational field that's pulling down. In terms of the oscillations, if you pull it, everything is exactly identical, except for the fact that it oscillates around the new equilibrium point rather than the old equilibrium point. And so because I had kind of just invented that problem in my head as we were doing the first part of the review, and then we just did it and didn't really think about it, I just treated it that way. The correct solution to the problem, though, is recognizing that even though it's just got a new equilibrium point and the oscillations will only have shifted down a little bit, the potential energy in the spring doesn't shift that way, because it's not linear, you know what I mean? So it's quadratic. And so the amount of energy that I store, so here's an example, the amount of energy in it right now versus if I stretch it down, that difference in energy is different than the difference if I shift it down another unit, you know what I mean? So you might imagine, because it's quadratic, you might say, if I pull it down 1 meter, the change in energy is 1 joule. But if I pull it down 2
then the change in energy will not be another joule. It will be 4 joules. And if I pull down another one, it'll be 8 joules. Does that make sense? Or no, 9 joules. Right? So you have to take into account the initial stretch length of the spring and count that in with the kinetic or the potential energy. And when you do that, you get an answer that makes a lot more sense.
How likely would we be to see one?
0.
Okay, cool.
But it's the concept of combining the potential energy and the, I mean, I'm not saying that you won't have to combine potential energy and spring energy and momentum and stuff like that, because that's entirely possible that you might have to do something like that. You won't obviously see that problem. And if you do see it, it probably won't be sort of compounded by the gravitational bits, right? Which is really the sort of screwed up part. So in the sort of overview that I said, that I spliced in that actually solves it correctly, I solved it correctly and then said, if you want to do a real practice problem that is more representative of the concepts that I wanted to show you, just do it horizontally. So it's connected to a wall. So the gun is like this. Fires the bullet here. In that sense, in that case, right, it's easier because it doesn't have to deal with the whole initial stretch thing. But if you wanted to do it, the solution that's on the video that is correct. Okay. Good. So what else? We got. Someone's got something. Yeah.
Can you know the relationships that when you know about like pistons?
Pistons, right. Hydraulic stuff.
Well, pistons is the thing you have.
So the idea is the following, that if I have two, and this one has area A1, and this one has area A2. So imagine I move this guy down by some distance. X1. Okay. So how much water have I forced into this side of the tank? In volume. So it started here, I push it down, right? So the amount of volume I forced into this side, this delta V, is equal to A1 times X1. Okay? So, assuming of course it doesn't burst, and it pushes this guy up. So what distance then has this one gone up? This distance will have then increased, so we'll imagine that the walls of the tank like this. So we imagine then this guy goes up by some distance, and we'll call that distance x2. Okay. And so what that means is this must be A2, x2. Because that's just the amount of volume that's gone in. This relies on the fact that when some volume of water leaves this side, it goes into this side, which is really the requirement that the fluid is not compressible. So I can't take some volume of water and then make it a smaller volume without changing the amount of water that I have. Or volume is conserved, if you want to think of it that way. So whatever leaves this side goes into this side. A1, x1 leaves, A2, x2 is what comes in, and they must be equal to one another. So that's fine. So I have this equality. So obviously, right, if A1 is really small compared to A2, then X1 is going to be large in comparison to X2. So I'll have to push this guy down really far. If this area is 5 times that area, I have to push this guy down 5 centimeters to make this side raised by 1. But I can do it. So this is a direct geometrical relationship that relies on the incompressibility of the fluid there. If I have a force that I'm applying to the thing, so the force is equal to pressure P times the area. So the force that I apply to this side is equal to the pressure that I apply to that side times the area. But if I'm pushing down, so if I'm applying some pressure here, that pressure is then transmitted everywhere in the fluid. Okay? So the pressure everywhere increases because of my pressure just here. Pushing down like this increases the pressure. So if there's a hole in the side and I had a Band-Aid over it, it wouldn't matter where the hole was. When I push down, the water would start to break out. Okay? So that means that the pressures on this side and this side must be equal to one another. That is the requirement that the fluid transmits pressure, which is actually related to is essentially the same as saying the fluid is not compressible. So if that's true, then the pressure on the first side is equal to the pressure on the second side. But the pressure on the first side is the force divided by the area. And that's equal to the force divided by the area. So if the areas are different, the force is different. So the idea behind hydraulics is if you have F1 over F2 is equal to A1 over A2. Or F1 is equal to F2 times A1 over A2. So the idea being, I can get a really big force compared to what I apply. So I can apply a 1 Newton force and get a 10,000 Newton force on the other side, as long as the area on my side is 10,000 times smaller than the area on the other side. Okay? So that's all it is. So the pressures are equal, which means the forces are the same. So you get this. But you also have to recognize this part, right? Which is to say, if the area is, if one side is 5 times the size of mine, when I push down, the force I apply is amplified by a factor of 5. But the distance that the thing raises up is decreased by a factor of 5. Or, if you want to think of it another way, the amount of work I've done is the same. So I can't get any work out of this system. Okay? So whatever, if there's a car on here, its work is the force times the distance. If I push my side down, I've applied some force over some distance, and then the car gets raised up by applying some force over some distance. The force that's applied is way higher, but the distance it travels is way smaller, and they cancel. And so I haven't gotten any work out of this. So it's just a sneaky way to amplify your force, but you can't get any work out of it. Anything else?
What should we do if we come across a question that says like there is slipping like in the last exam?
That there is slipping?
Yeah.
At least you won't quantitatively have to do anything.
Okay.
Qualitatively, you may have to do something in the sense that they might say there is slipping. So, or maybe they would say there's a cylinder that is sliding down a hill, right? And there is slipping. Compare that to a situation where you had a cylinder rolling down a hill and there was no slipping, in which case would it be going faster? The center of mass, in which case would the center of mass be going faster? Something like that. That's equivalent to, by the way, saying, so if we have a case where there's no, so by the way, the fact that there is no slippage corresponds to the idea that the coefficient of friction is high enough to handle the stress that's being placed on it.
Static.
Yeah, the static friction. If the static friction is really, really large, then it's always going to roll without slipping. But if the static friction coefficient is small, then you can overcome it and burn out, or you could skid as well. Both of those are possibilities. But if it's high enough, then it will be perfect roll, or it will be no slip. So you should recognize that the slippage is related to the amount of friction that's there. If there was no friction, it wouldn't slip at all, and it would just be essentially a thing rolling down with no rotation, right? Because there'd be no torque. It's
gravity is acting on the center of mass, but if it's acting on the center of mass, it doesn't provide a torque about the center of mass. So if there's no friction, then there's no torque, then there's no rotation, it just goes down like we were doing a point part. But if there is friction and it's sufficiently high that there's perfect roll, it's going to decrease. And anywhere in between is going to be like a continuum. So if there's a little bit of slipping, it'll be somewhere in between a free falling object or a free sliding object and one that's in perfect roll. So the free sliding one is the fastest it'll ever go. The perfect roll is the slowest it'll ever go. And any amount of slippage in between is going to be.
Are you gonna have to know damping forces?
You'll have to at least understand how they work. The idea that when you have, obviously, so by damping, you know, we're talking like fluid friction, right? Air resistance or resistance of some arbitrary fluid. And you have to understand that it essentially just sucks energy out of the system. Right? That whatever you have when it's undamped, it's just going to slowly pull energy out when it is, depending on the level of damping. The other thing you might need to understand in respect to fluids and stuff is, I know you guys talked about Archimedes' principle and things, how they seem lighter when they're inside a fluid, and that's because of the, it's because of this relationship that so you have a tank of water. So let me draw this real quick, because it's actually kind of a neat thing to understand. Because independent of like shape or anything like that, if I have some kind of object in the water that's completely submerged in the water, or the fluid, right, that's the row, and I'm going to sort of color it in. So this is not the same as the weight of, or this is not the same as the fluid that it takes. So this might be a human in a pool or something like that. Okay. Or actually remarkably close to water, but yeah, human in a pool. So I might ask you, if let's assume this thing isn't moving, or yeah, so we'll assume for a moment that it's not moving, so it's sort of in equilibrium bobbing there. So let's say it's like connected to a string. So it's not allowed to move, so it's just sort of drifting in the water, but it's connected, so it's not allowed to slow down. And the question is, what's the tension of the string? Obviously, you know, if the tank wasn't there, it would be the weight of the thing. But what you want to ask is the weight of the thing, does it stay that, or does it get lighter? And you know that it gets lighter, right? Because all of you have been inside the pool and lifted somebody, or jumped around and moved off the bottom, and you know that you feel lighter when you're inside the pool. And so this is what's going to explain why. What you want to imagine is this exact same shape. Being outside it. So imagine that you've removed this shape of water and you've just put it outside the tank. Gravity is pulling this thing down with whatever this, I'm sorry, this is water, whatever fluid, M fluid times G is the force with this gravity is pulling this lump of fluid down. There must be some force pushing it up, which we call a buoyant force. Because if this was just water and there was nothing in there, it would be in equilibrium, it wouldn't be moving around. So if this was completely gone and this lump was just made of water, then the force on it would be zero, the net force on it, which would mean that there must be some kind of buoyant force going up that is equal to the weight of the water. So if you put a lump of something like a lump of coal in there that's not water, the force is no longer necessarily zero. But the buoyant force is still going to be m fluid times g. Okay? So a good way to think about it is the buoyant force doesn't care about what the object is. It cares about the shape of the object, and it cares about the location of the thing. But really, the thing that you have to understand is the buoyant force on the object is equal to the weight of the water that isn't there anymore, or the weight of the water that has been displaced. Okay?
So if this was, for example, I didn't know what this shape was, it was weird, but it was had a total volume of 1 cubic meter. I don't know what this object is, I don't know its density, I don't know its weight, I know nothing. What I do know is that the mass of 1 cubic meter of water and fluid is the density of water times that volume, which in this case would be 1,000 kilograms. Which means that the buoyant force on the thing is equal to 10,000 newtons. So if you have an object that occupies a total area, or a total volume of 1 cubic meter, and you drop it in a tank of water and fully submerge it, there will be a force on it, a buoyant force up, that's equal to the weight of the water that you displaced, which in this case would be 10,000 newtons. Now, if this is denser than water, then it will still sink, but it will have that fluid force pushing up. So the net effect will be that it feels light. Right? So if this had a total weight of, let's just say weight equals 15,000 newtons. Okay, so it's a big chunk of lead or iron or something like that. And you drop it in there, then the net force on the thing is still going to be down, but it's not going to be 15,000 newtons anymore, as it would be if it were just hanging in the air, but it would be 15,000 minus 10,000 up, which would mean that the weight apparent, right, to me trying to lift the thing would be equal to 5,000 newtons. So that's why things that in the submerged in water feel light.
How did you get the 1,000 and 10,000?
That's the density of water, 1,000 kilograms per cubic meter. And FB is G times that 1,000, so 10,000. Okay. It's also possible that the weight of this is lighter than water, so it's less dense, like ice or styrofoam, in which case the net force is going to be up, and it's not going to stay under. So you try and push it, but you let it go, and it starts to fall up. And so it will reside at a place where enough of it has submerged to offset its weight. So you can calculate what volume of the thing will be underwater when it's just bobbing on the surface based on its weight and the weight of the water that it would have displaced. Okay? So if something is denser than water, it will sink but seem lighter. If it is if it is not as dense as water, it will float and it will bob on the surface, and the amount of it that is submerged, that volume is equal to the volume of water that would be required to equal the thing's weight. Yeah.
So you're saying the object has to be less dense than water, but like what about ships? Because they're made of like iron and stuff.
They're hollow.
Okay.
So they're not less, they're actually considerably less dense than water. The skin of them is denser than water. But there's a big open bit inside of them, and so you have to take that into account as well. So the ship is considerably less dense than water. If it were made of, if it were a giant chunk of iron, it would just the same way. Okay? Fluids, Archimedes, buoyancy, and all that stuff. Anything else? It's tough, man. You guys have a lot of stuff to learn. I believe it. I know, I didn't look at it.
Are there two versions?
Yeah, no, because everyone's saying it at the same time.
Could be A version and B version.
Is the A version harder than the B version?
So I guess there are two versions of it, yeah, probably, but it's almost universally.
I mean, let's be trying to get ripped off in there.
Well, good luck if I
I don't see you or talk to you.